inconsistent and dependent systems when it comes to matrices. In other words, how does the matrix show us if a system is inconsistent or dependent? Our objective? We want to identify those systems that do not have one solution. In other words, this solution is not an ordered pair or an ordered triple, etc. from the TI's reduced row echelon form operation. Let's recall a couple things we've already talked about. The solutions to linear systems will be one of three types. They'll be consistent, in other words, an ordered pair or an ordered triple solution. You'll have one solution. They'll be inconsistent. You have no solutions. When we had two equations and two unknowns, those two lines were parallel. As we're dealing with three equations and three unknowns, those will be three planes that are parallel to one another. And then finally, they can be dependent, which means they have an infinite number of solutions. Again, if we're dealing with lines, one line on top of the other, coincidental. If we're dealing in three dimensions with planes, then all three planes are on top of one another. So, algebraically, we worked with this in a previous video. We were dealing with linear systems in two variables. We recognized inconsistent and dependent as follows. If we ended up with a nonsense statement, for example, 0 equals negative 12, that told us the system was inconsistent. We had no solution. Again, those lines were parallel. If we ended up with an always true statement, for example, 10 equals 10, that told us the system was dependent. In other words, we had an infinite number of solutions, and again, that was one line on top of the other. Okay? Well, when we're working with the matrices and the TIs and the reduced row echelon form in the TI, we're going to look at the bottom row, and it's going to tell us if the solution is inconsistent or dependent, and it's going to look remarkably like these two things right here. So we're going to focus on that bottom row when we're doing this. Let's take a look at a couple of examples. One, of course, will be inconsistent, as you might imagine, and one will be dependent. Okay, let's solve this linear system using the rref, reduced row echelon form operation. So we already have these in standard or general form. We have coefficients for all of our variables. So we can rref an augmented matrix, which would be 1. The first equation is 1 coefficients, 1, -1, -2. I'll draw a dotted line, and we have a 2 as the constant. The second equation is going to give, it has a 2 as a coefficient for the x, a -3, and a 6, and the constant is a 5 on the right side of the line. And then finally we have a 3, -4, and 4 as coefficients to the third equation, and the constant is a 12. Let's remind ourselves, these numbers are coefficients to the x terms. These numbers are coefficients to the y terms, and these numbers are coefficients to the z terms, and those, of course, are just the constants on the right. And let's also remind ourselves that this is a 3x4 matrix. Okay, let's do this one the longer way for those who don't have the shortcut. I'll go into here, and so I need to, hope I got that straight. I need to go into my matrix, so second matrix, and I need to edit a matrix. And I'm going to edit matrix A because I don't have any use for whatever's in there. It's already 3x4, so we can leave 3x4, and we can go to the first entry in row 1. And that entry was a, what was a 1? I'm going to put this in there, but I'm covering it. And my light, my overhead light is making things a mess. So I'm going to use my notes off to the left here. 1 and then -1, these are those coefficients, and then -2, and then in column 4 I have my constant of 2, and then I'll continue row 2 would be 2, -3, hope I'm getting this right, 6, and that constant was a 5, and then 3, -4, and then 4, and the constant in the third equation was 12. So now I've entered my matrix. It is matrix A. So I'll get out of the matrix, second quit. I'll go back into matrix, second matrix. Now I want to do some math on matrix A. So I'll go to the math. I'll scroll till I get to rref, press enter. I'll go back into matrix and I'll choose matrix A. I want to rref matrix A, and that's what I come out with. Okay, so 1, 0, -12, 0, 0, 1, -10, 0, 0, 0, 0, 1. Okay, so it's hard for you to see. I think my light's kind of in the way a little bit. Let's try that. There's better. 1, 0, -12, 0, 0, 1, -10, 0, and 0, 0, 0, 1. Let's write that down. So what came out after I row reduced echelon formed it? That's terrible English, but you get the idea. I got a 1, 0, -12, and again I'll use a dashed line to separate my variables from my constant. I got a 0, 1, -10, and then that had a 0, and then I got a 0, 0, 0, 1. Let's remind ourselves that this is the X column, this is the Y column, and this is the Z column. These are coefficients, and this is the number column. Okay, we want to look at the bottom row. Here's the bottom row, right there. Okay, the bottom row. What does the bottom row tell us? The bottom row tells us that 0 X's plus 0 Y's plus 0 Z's is equal to 1. Well, that is nonsense. 0 does not equal 1. And that's what it tells us. 0 equals 1. Well, we saw that. We saw that in our 2 by 2 as I look up the paper a little bit right here. When we had a nonsense statement, it told us the system was nonsense. There was no solution. It was inconsistent. Well, this tells us the exact same thing, in this case, for a linear system of 3 variables. So we have a nonsense statement. This tells us that the system is inconsistent, if I can spell it correctly, and that there is no solution. In 3-dimensional space, that means we have 3 planes, and those 3 planes are parallel to one another. There's no touching going on with those 3 planes at all. Okay, let's take a look at one more example. Whoops, wrong paper. For dependent systems in which we have infinitely many solutions. Okay, so here we are. And I'll do this one with the shorter cut on my calculator. Give me a moment here to get my notes set up. There we go. Okay, so we want to solve this system, again, using the TI's row-reduced echelon form operation. We want the TI to do all that substitution and addition for us, so we don't have to. Okay, so I've got my system. I notice that I have all my variables represented. I have my constants. I'm in general or standard form, so I'm in a good place to build my augmented matrix and then row reduce it. So again, my coefficients, 3, -4, +4, dotted line, and then my constant, just using a dotted line again because there's no line in the calculator. That just helps me keep things separate. Coefficients of equation 2 are 1, -1, -2, and then the constant is 2. The coefficients of equation 3 are 2, -3, 6, and 5 is the constant. Again, these are the X coefficients in column 1. These are the Y coefficients in column 2. These are the Z coefficients in column 3. And those are the constants in column 4 on the right side of the equal sign. And let's again recognize this is a 3 by 4 matrix. Okay, so let's use my shortcut. And listen, maybe I can slide this up a little bit better and put this here, and you can kind of see it. I still got my overhead lights kind of messing things up a little bit. Sorry about that. If I turn them off, we can't see anything. So let's go into here, and I'm gonna do the short way, which means go into matrix, go into math, and choose row reduce, echelon form, and then my F3, my matrix is already set for 3 rows and 4 columns, so just press OK, and it pops right up for me. And I'm going to put this data in there, 3, -4, 4, and 7, and then 1, -1, -2, and 2, and then 2, -3, 6, and 5. Close up that parenthesis. So much easier with that shortcut key on with the F3 on my calculator. Press enter, and again, you probably can't see that, so let's move it over here. And what came out was 1, 0, -12, 1, 0, 1, -10, 1, 0, 0, 0, 0. Let's write that down. So I'll use my notes, and what came out of this was a 1, 0, -12, and a 1, a 0, a 1, a -10, and a -1, and a 0, 0, 0, 0. Let's just separate these with a dashed line so it's a little easier to read. Let's recall that this is the X column, the Y column, the Z column, and the number column. And let's focus on the 3rd row, right there. You also notice we got numbers up here we shouldn't have. But anyways, let's focus on that 3rd row. This tells us 0x plus 0y plus 0z is equal to 0. Well, no kidding. This tells us that 0 equals 0. Well, that's always true. You know, that's a given. No matter what x, y, and z are, 0 is equal to 0. And we saw a similar thing when we looked at our 2 equations and 2 unknowns systems. So when we see this, we're talking about dependent. In other words, we have an infinite number of solutions. Okay? So basically what you want to be aware of, all right, what you want to be aware of is what's happening in this 3rd row between these 2. If you really want to focus between these 2 right here. If we've got a 0 in this space, I'll go back to here. If we have a 0 in this space and a number in this space, we have an inconsistent system. This should be, a consistent system is z equals a number, 1 and a number. If there's a 0 here and a number, the system is inconsistent. No z's equals a 1, and that's not going to happen. Okay? Again, in a dependent system, no z's equals 0, if I may, and this is a dependent system right here. The 3rd row, when we have a 0 in that spot, we recognize that we have a dependent system or an inconsistent system.